Last lesson, we looked at this idea of what we call conditional probability. Harry, can you remind me again? Yes. This idea of a conditional thing, what's actually happening here? What was the example we looked at with this Venn diagram?
One thing is true, the other
That one.
Say it again, Laura.
One thing is true.
A given B.
Yeah.
Right, so given is the word that I was kind of using. So this kind of means A given B. So in this situation, A given B means that, for example, given that B is true, so given that this person has red peas, what's the chance that A is true, that they have an iPhone? And what actually changed with the probabilities? Like, what were we changing at this point? We were changing the sample space, right? And there was that kind of restriction imposed upon it. Just to kind of clarify, right? With this one over here, we can do it in two ways. You can just look at it from the Venn diagram. You can look at it visually, say, okay, there's only two people with red peas, and so that's going to be one person who has an iPhone here. So it's just 1 over 2, okay? But this definition over here, when I'm talking about P, that's representing the probability. Okay, so let me just show you just carefully how I'd actually do this using probabilities if we didn't necessarily have that visual diagram, right? So what's the probability that I can have both A and B? So I have an iPhone and a red piece. What's the probability in terms of the whole class? Yeah, it's just 1 out of 11, right? So that would be 1 out of 11 because that's P, the probability of A intersection B, right? And what's the probability of B? Well, there's 2 people here. Yeah, it's 2 over 11. If you put that into your calculator, or you realize, hang on, you can just take the reciprocal when we're doing that, that becomes half, right? So can you see that's how it actually kind of works, right? Let me give you another one. I want to see what you think. Oh, sorry, before I give you the other one, we can write this in a similar way as well. I didn't actually get you to write this down. We can also write it like this. So this one you do need to write down. P of B given A, right? What's that going to look like? It's going to look like a very similar thing. So think about it from the other perspective. If I now have, I'm looking for the probability that they have a red piece, given that they have iPhones, what's my new sample space now?
9.
Right, or the probability of A, right? Probability of A. I still am looking for the intersection though. So because remember, A intersection B, that's the same as B intersection A, right? Those mean the same thing. Okay.
Close that bracket first. On the bottom one.
Like that? That's all right. Let me give you another one. I want to see what you think. Let's see now, if I flip a coin, for example, right? Right, I get tails. This is a kind of a different scenario. I get tails. Again. I get tails again. Okay. So given this is true, this is given, right? I've flipped 2 tails in a row. What's the probability now that I'm going to flip a heads? So the way I'd write this out is I flipped heads. Oh, sorry. Let me say that again. So I'm looking for the probability that I'll flip heads given that I flipped 2 tails. That's the question that I posed to you. Have a think about it first. So let me explain it again. We flipped 2 tails. Given that this is true, what's the probability that I flip heads? Have a think before you say anything. Is this similar to this situation here? What's similar about them? Yeah, I can't have, I can't, just kind of deciphering this, I can't have heads and tails at the same time, right? I can't have heads and tails at the same time. That's something that's true, right? So in that sense, they're kind of different, right? I can have someone who has a red piece and their iPhones. I can't have flip heads and tails at the same time, okay? But something that is a little bit different is, does anyone actually think they know the answer to this before I kind of go into it? If I flip 2 tails already, if I flip a heads again, what's the chance of, I'm looking for the chance that I flip a heads, yeah.
Wouldn't it just be half again?
Why do you think it would be half?
Because the fact you flip 2 tails doesn't actually affect the chance of getting a heads or tails next time.
It's actually a bit of a trick question. Can you see that, right? Because it doesn't matter how many times I flip this coin, whatever results I get, the next flip is always going to be 50-50. Right? And that's because a coin has no memory. Right? A coin doesn't remember what the previous results were. Okay? It only knows that it's got two sides. So this kind of situation, we expect our answer to be half. And this is kind of weird, right? Because that's just the probability of flipping your heads. This is something we call an independent event, which is exactly what James was talking about. Yeah, an independent event is when the probability of something doesn't affect future events. Right? This is independent. So the probability that doing something doesn't affect future events. Right? In this kind of sense, what's happening? We're actually changing probabilities because once you restrict the sample space, you're going to change the probability that they can pick an iPhone. Okay? But let me just show you, bless you, let me just show you that this definition still holds true. Okay? Right, so we expect the answer to be half. How do we actually get there? This is kind of weird because we're kind of working backwards. We've got the answer already, but how are we actually doing that? Right? Let's think about this definition here. Right, what's the probability of flipping two tails? Yeah, 1 out of 4, because just half times half. Or just 1 out of 4. Now, if you think about what should go on the numerator, what should go on the numerator is the intersection of these. And when I'm talking about the intersection, the language that we often use is and, right? So if you want to think about the probability of flipping heads, tails, we can take Alora's idea still. And we know that the probability of each of these is still half, right? So when I'm thinking about these independent events, how do I calculate their probabilities together? If you think about intersections, all you're actually doing is you're just multiplying, right? If you think about the intersection, you're just multiplying. So for independent events, the probability of A intersection B, what you're actually doing is you're just multiplying them together. That's all you're doing, right? So this one here would be half times a half times a half, or 1/8. Okay, so let's kind of put this together now. Using this definition here, right? So we're kind of putting all this together. P of H, given that these two tails have already happened, what's that going to look like? Well, it's going to be the intersection of these, so these happening together, which is this probability here, 1/8, all divided by, what's the restriction? What's our sample space? What's the probability of the two tails happening? We already have that. That's just 1 on 4, right? Can you see that? That's just 1 on 4. Put that in your calculator for me.
Is that half?
Let's find out.
I think it is.
You think it is? Yeah, if you do some reciprocals, or you just put in your calculator, you get that it's half. So, with independent events, okay, the probability is just going to be whatever this is going to be, okay? If you want to see that a bit more formally, look up here. P of A intersection B is just P of A times P of B, right? So go back to this definition. This is kind of like a little proof, right? Question, yeah.
So you're still not working out for nothing?
Well, it's to show you that why this occurs, right? It's to show you why this occurs, okay?
But you don't need to do that, you just need to do the probability of the A.
Yeah, you do, but sometimes you need this particular definition because you can actually find hidden information using this definition, okay? So let me give you an example, right? So let me show you first. Here, A given B is equal to P of A intersection B all over P of B. And for example, we can see that this here is just P of A times P of B, only for independent events, by the way, yeah? Divided by P of B. And what do you notice happens here? Yeah, because these would just simplify out. It would just be P of A, right? And you may be wondering, hang on, why couldn't I have just told you that, right? But because some of these questions, they're going to rely that you know this knowledge very well, right? So for independent events, okay, if I want to find some conditional probability, I can actually just look at the probability of that individual thing occurring, which is why I was flipping coins, right? It doesn't matter what happened previously. We can actually just look at the probability of flipping heads. Let me give you an example question that they will often ask. Okay, so why am I writing that down, right? It's important to note that this fact here that we've just kind of shown can only be used if they're independent events. So we can't really assume anything, okay? But it's something to keep in mind as we're kind of looking at these problems. Another thing that's to note is that A given B and B given A, they're not the same, even though they look quite similar. We saw that with the Venn diagram example. You actually see that very clearly with this definition, right? Although the numerator is the same, we've got denominators that are different, right? Okay, so let's think about that as we're answering these. Harry, for the first one, what did you try to do?
Well, I did 0.24 over 0.6.
Okay, so you know that A given B is probability of A intersection B divided by the probability of B. So it's just 0.24 divided by 0.6. Do you want to simplify that out for me a bit?
No.
You can check in your calculator.
It's 24 over 1. Could do that.
4 over 1, so the number became bigger.
Oh, yeah, I'm an idiot, so.
That's
You
all.
get it down to 24 over 60.
Is that better? Yeah.
Yeah, 24 over 60.
Do you want to put in your calculator?
No. It's 24 over 60. I'm not simplifying it.
I think there's something in common. Four more we can do. James, help us out.
It's a 0.4.
0.4. I'm happy for that. If they're giving you decimals there, probably want to leave them in decimals.
Did you hear that?
Joel, next one. Have a go for me. What's different about this one?
It's 0.24
Yeah.
over 0.4 this time, which equals 0.6, which is P of B.
Yeah, not too bad, right? So
Wait.
we've got 0.24 divided by 0.4, right? Because that's our definition. P of A goes in the denominator now, and you said that's equal to 0.6. Okay, starting to see a pattern here, right? Determine if they're independent, right? How do we know when events are independent? Definition-wise, it's when the probability of one thing doesn't affect the other. What about calculation-wise, though?
The condition, condition of both of them would still just be the same as one.
Exactly right, and you can sort of see that here. I would always go back to this definition here is probably the easiest to use, though. If the probability of A intersection B is equal to the probability of A times the probability of B, then we know that they're independent. So for this one, right, P of A times P of B, that's just 0.4 times 0.6. And it does end up being 0.24, which is P of A intersection B. Right?
So it is independent.
So it is independent. Right? And I think you started to see that as you were answering these problems. Important to note that we can't just always assume they're independent, right, unless they tell us or unless we show it through that one. Right? One more example, and then I'll get you to go on with the textbook exercises. Callum, can you read this guy out for me? This one up here.
If probability of A equals 0.7 and probability of B equals 0.2, and they are independent, find probability of B given A.
Okay, so we've got information, we want to work out what we need to do, right? So for this one, right, I always go back to whatever we're presented. P of B given A, what's my formula for that? Well, I've got that over here. Where do I go from here then?
You can put the 0.7 on the bottom.
I could, let's do that. Because I know that's P of A.
And then
Still a bit stuck there, aren't I?
So is that independent, so should the probability just be 0.2?
So if they're independent, then I'm thinking, oh, shouldn't the probability here just be 0.2? Because I know that fact, they give that to me, right? And that's exactly what we can do. If you just want to make sure, right, think about your definition, right? Your definition of A intersection B or B intersection A, which are the same, is if they are independent, we can just multiply them together, right? So 0.7 times 0.2, just to clarify, yep, all right, and they do simplify out to 0.2. But as Callum said, if you know that they're independent, you can just find the probability of B, and that's 0.2. It is worthwhile, if you are going to do that, just kind of put a brief explanation. Because they're independent, we can just find the probability of B, okay? So using this knowledge, they're gonna ask you a lot of problems like this that rely on that, okay? But be careful when applying them because you have to make sure that they're independent before you can actually do any of this, all right?